let me see. I want to share my entire desktop. Share it. Okay, that will do. Show active speaker video. Nope. Oh, you're not talking. Blah, blah, blah. Right. I'll just leave myself small up in the top corner there. And now, why have you jumped over there? Get rid of that. Ooh. Well, that's an improvement as long as you stay there. Oh, and I need to get up chat. Where's chat? Okay. And of course, chat goes behind that. What's that? I would have thought, since I'm the active speaker, my face would show up there. Oh well. Let's get rid of it altogether. Okay. I just checked. There's someone awake. Maybe there's no one awake. Yes. All right. Cool. Good. Okay. Let's go. All right. So the quiz 1 marks are now out. Normally they will appear on Monday morning. So they're normally due on Friday, and the results will appear on Monday. If I remember to push a button in WebCMS, you can't schedule. I can talk a little bit about assignment 1. I wasn't planning to, but let's see if I can make something up as we go. I'll have a look at, I'll show you complex.c and complex.source. All right, so assignment 1, making base data type. And that means it's really low level and it's a little bit like the integer type. And in fact, I'm pretty sure the integer type is defined like we're defining sets in assignment 1. So what you actually have to do for this assignment, sets, constant set values are going to be strings with a certain structure. Let me just, where am I? Week 3 seems like a good place. So here's the very simplest set, the empty set. There's a set with, we can put in 1. There's a set with 1 element. There's a set with 3 elements. The way you need to handle variable length types. Oh, you'll have to work that out. Or you'll have to look at some of the other examples that do implement variable length types. I mean, that's part of the challenge of this assignment, to work that out. All right, here's another set. And here's another one. Oops. Which in fact is the same as the one above it. So one thing that you ought to be doing with these sets is converting them into some sort of canonical form. As I said, there are other examples of Varlen types. All right, I will have a look at complex.c and complex.source in a moment. Maybe I can make it less opaque. I don't know. And of course, the sets can be arbitrarily large. And I'm just typing random crap. There, oops, shouldn't be a trailing comma. Okay. So one thing you'll have to do is write a parser for these strings. Ooh, and that's incorrect as well. There should never be two adjacent commas. So this parser will have to be able to take some string like this and convert it into a set data structure. You have to define the set data structure yourself. You have complete choice about how you do that. You could define it as a string. You could define it as, what else? Sequence of bits, although if you do it as sequence of bits, oh, all right, Curtis. If you do it as a sequence of bits, then you're going to put an upper bound on the size, which we don't want unless you implement flexible length sequences of bits. Right, so first thing, take this string and convert it into an, well, interesting, into an internal representation that I would argue, in fact, I won't put quotes because this is an internal representation. And so this set has got 1, 2, 3, 5, 6, 7, 8, 9. What else has it got? 43 and 54. So that could be an internal representation. I don't understand what you mean by single byte array, byte star. Okay, fine. Will there be a big O limit for our set? Yes. All right, so your internal representation is going to have to be, all right, as Curtis said, a sequence of bytes. How you want to structure that is up to you. You could do it as a string, so effectively wrap quotes around this thing. Or you could do it as some other kind of structure. Such as a sequence of int values. So a sequence of 4-byte chunks where each chunk represents a member of the set. I never said single allocation. It could be a sequence of bytes. I'm not telling you how to do it. Part of the deal with this assignment is that you work out what's a suitable data structure. And before you do that, you'll need to think about the operations that you're going to have to implement on this data structure and think what might be a suitable representation. So, for example, if I did store things in order, and I'm trying to work out whether something is an element of a set, yeah, all right, sure. You could try and do it as a tree, but the tree will have to be, what's the word? Flattened, effectively. Yeah, contiguous in memory. Oh, there's a standard phrase for describing it. No, not just contiguous. It's, oh dear. Yeah, anyway, it's when you take a tree or a graph structure and you represent it as a single sequence of things. Now, hey, sure. One thing you could do, potentially, is you could store it in an internal representation that was easy to convert to a tree, so that when you're doing this kind of searching stuff, you take your internal representation, make it into a tree, and then use the tree to implement the operation. Yes. Oh, isn't that what I said? Serialize. Thank you. That was the word I was trying to think of. Yeah, serialize it. So some kind of stored, so all right, there's two deals here. There's your input representation, which is this string. There's the stored representation, which could be a string as well, or perhaps while you're building your internal representation, you do it as a tree, and then you serialize the tree and you store that. I mean, going back to Curtis's original point, yes, ultimately we store an array of bytes in memory and store it on disk. Right, so this input representation, which is a string which starts with a brace, ends in a brace, and has positive integers separated by commas in between. And there can be an arbitrary amount of space between all of those components. So here's another possible representation of this thing. So it's the same set as the one above. So essentially you ignore all the spaces when you're doing input, right? So you read it in, you form an internal stored representation, which you initially form in the memory, but you have to make it into a tuple, or sorry, into an attribute value that can be stuffed in a tuple and then stored on disk. All right. When you're doing searching and testing for set membership and testing for set inclusion and so on, you take the stored representation from disk and then you can convert it into a convenient representation for whatever operation you're trying to do. If you think you'd just rather work with strings all the time, then sure, you could do that. I'm not sure how super efficient that's going to be for some operations with large sets. I mean, one deal with this is sets tend to be pretty small, so Even if you come up with an inefficient representation, you're probably not going to pay a big cost in execution time. And yes, there will be an execution time limit for operations in this assignment. So you can't have an absolutely hideous complexity for whatever algorithms you're using. Like I said, most of the time the set's going to be relatively small. That's a small set. Even 100 elements in the set is still small and is never going to trigger an execution time limit unless you write a horrible searching algorithm or a horrible subset comparison algorithm. We will have a couple of large sets though, so potentially that's an issue. Obviously then, a couple of large sets in a large test set, large collection of test data, if you fail for the large sets, you're not going to lose many marks. So if you can get it working for relatively small sets, that'll get you most of the marks. If you can get it working for very large sets, that'll get you the rest. Okay. All right, what else I had? Oh yeah, we had to change the deadline, move it forward 3 hours. Oh my God, everyone jump up and down and protest. But the head of school decided that we shouldn't have assignment deadlines outside UNSW operating hours. And basically UNSW can start classes, I think, at 8 a.m. and the last class ends at 9 p.m. So it's moved forward from midnight to 9 p.m. So gosh, you'll have to do 3 hours extra work between now and the 19th of March. I don't think I've put that in the spec, but I haven't put it in the change log. I'll do that sometime. All right. I'm still getting questions that suggest people are still a bit lacking in Unix skills. And one question that I've had a couple of times is my ZID doesn't appear in this list, which is all of the directories under /server. And the reason it doesn't appear most likely is because you didn't run that command. When you run that command, it creates your directory. If the directory already exists, then it basically does nothing. So if my directory didn't already exist, then I would find a directory called JAS now under /server. Yeah. All right. So you need to start learning where things are under Postgres. And here's the top level of the Postgres distribution directory. Doc, yeah, the manual's located under there, but we've already got a nice online version. And then we've got source. Now, if you're a dinosaur like me, you won't use an IDE, but you will have, you can create a tags file. There's a command called ctags that'll create one of these things. And then if I wanted to find something like the definition of heap tuple, then I can run, well, all right, this also assumes that you're a dinosaur enough to use Vim or VI, and it will take me straight to the definition of heap tuple, which turns out to be a pointer to heap tuple data, which fortunately is defined up there. C-scope, yeah, all right. Fine. I always thought C-scope looked a bit like an IDE, too much like an IDE for my liking. You can use C-scope if you want. All right. Yeah, so we pointed you at this directory, source/tutorial, where there's a couple of examples of building how do you use C-scope? You type the command C-scope, presumably, and oh, interesting. Let's see. We can do a test. Could not find the symbol. How do we set things up, Curtis, to make C-scope work? Does it require a tags file? Thanks. Oh, really? Minus R. Okay. Beautiful. Oh. Don't know what it was doing there. In any case, I'm not in a useful directory. So that apparently builds something like, yuck, why does this look so messy? Is my window not wide enough or something? Beautiful. As you can tell, I never use C-scope, and yeah, I don't know how I've ended up with 3 panes. See, no wonder I don't use it. It's, oh, yeah. Can't even kill a damn thing. Great. All right, I'll never be using C-scope, I can tell you that. I'm happy with C-tags. Yay, Curtis, yeah, sure. How do I get rid of that? Maybe that's like that too. Ha, good. All right. All right, so we're in source. We want to have a look at the tutorial directory. All right, so there are 2 aspects to building a new data type. Obvious. Yeah, thanks. All right, there are 2 components when you're building a new data type. You need to set up an SQL level interface, and it goes in a file called blah, blah, blah .source, which eventually gets turned into an SQL file. We'll have a look at it. And what it has to do, or it tells you what you have to do in here, blah, blah, blah. First thing, you need to create bindings to your input and output functions. And notice that, all right, the input is a string. In this case, I think these strings look like braces with 2 numbers in between. So this is implementing complex numbers. So it's like a pair of numbers. So the input is a string, character string, and the output is a value of type complex. Now you might say, what's type complex, and that's defined later on. Yeah, so you get a message telling you complex doesn't exist yet, but that's fine. All right, so there are two I/O functions that you need to implement. Complex in takes a string and produces your internal stored representation of an int set in your case. And there's also an output function which takes your stored representation and produces a string on output, which I would suggest, should be in some kind of canonical form, i.e. with all the values ordered, perhaps. It doesn't have to be ordered, but it does have to be readable by complex in. So I should be able to, print out or display the value of int set in, int set out. I should be able to do a select function on a table that contains int sets, and then I should be able to, if I stick quotes around the int sets that it displays there, I should be able to read them using intset.in. I think I'm just going to keep calling it complex because that's what's written in front of us. All right, so we need input and output functions. There are other input and output functions that work at a lower level that we're just going to ignore. They're for passing objects around internally. All right, so now we have to create the type. All right, so in this case, it's a constant size. It's actually it looks like floating point numbers. All right, it's two 8-byte quantities. Oh yeah, good point. This is the directory where all of this stuff is stored. All of this falls out in the wash when you use the make file. So you run make to build all this stuff, and the make file inserts the appropriate directory name here. So it's the directory where data, that's what I just said. All right. So creating the type, you need to say how long the type is. In your case, it's not a fixed length, so you won't be able to put that. All right, good-o. You then have to specify at least the input and output functions. I think these aren't strictly necessary, and certainly we're not writing functions for this, so I'm pretty sure you can leave them out. And alignment, your alignment is probably going, well, it depends how you represent things. If your internal representation is a character string, then you can have byte alignment. If your internal representation is an array of int values, then your alignment would have to be integer. Okay. All right, now this is just examples of using the data type. All right, thank you. Everyone watch the chat. Yeah, so this is just creating examples where we're storing values of type complex. So we create a table that has some attributes that are of type complex, blah, blah, blah. This doesn't actually define the data type, and you could certainly leave that out of your intset.source file. In fact, I would suggest that you do leave it out. of your intset.source file. Good. So why am I talking through this? All right, and then we want to define operators for the various operations on int sets. There's going to be a function that implements the operator. You can call it whatever you like. You know, here you could call complex. You wouldn't call it. Don't call anything complex, because you're not dealing with a data type for complex numbers. Call it intset dot union, or intset underscore union, intset. Right? And so you have to define a function, complex add, which is going to do, driving myself mad. You have to define a function called intset underscore union. Maybe I should just be changing this as I go. Ha! I have a plan. Goodness knows what this will do. It'll probably break it forever. I can't spell intset. Yes, I'm getting around to the .c file. Right, so now everything is int set. And I'm pretty sure, in fact, at this level, that I could have called it like that as well, since all the names are going to be mapped into all lowercase internally. All right. So let's roll back up. It won't be so confusing. Right. So inset in, inset out, inset receive and send we don't need. Create the type. You have to get the right alignment. Curtis thinks it's int 4. Could be. Oh, sorry. Whoa. I'm getting carried away there. That's only in fact, it probably worked for a lot of So if you represent the set internally by an array of ints, yes, thank you. So I don't want your stuff. So to define a data type, you don't need to stick test stuff in here. So I would personally remove that. All right, now if we imagine the inset add is inset union, well, that's the difference between the data type complex and int or float. Complex was the data type that's being defined in this file. So it's a different data type to int. Int is a different data type to float. I don't know if that answers the question, but they're all, the way complex is being defined here, they're all base data types in Postgres. Well, once you link everything in appropriately. Yeah, that's right. All right, so what we've done so far is we've defined input and output functions. We've given the bare bones of the type structure. All right, I don't think they're necessary, but I guess you'll find out. And then we need to start defining operators. So I can't remember. I should have looked at the spec before I came here. Oh, this is the wrong web CMS anyway. Yeah. All right, let's see. assignments. Haha. Assignment 1. This is a working draft. Hopefully you guys will find out enough errors in the next day or two that it will no longer be a working draft. Right, where are we? Set union, yeah, all right. So this double pipe symbol. So here we're implementing set union. And we can actually call a function whatever we like. I mean, it would make sense to call it union, but the union operation is kind of like addition on sets. So this will create the union operator, which we can use in SQL queries, and this will create the implementation of the union operator. Well, it'll set up a binding to a function called intset_add, which contains the implementation of the intset operator. One thing to notice, intset takes two values like this. It's going to take references to attribute values of type intset, which is your stored representation of intsets, and it's also going to return a value which is your stored representation of an int set. Now, what happens to this return value? Well, it kind of depends. I mean, if you're using it in a query, then whatever this value is that's returned is going to be returned, we set as part of the result of the query. And then in PSQL, it will invoke all right, hang on a minute. It will invoke intset out and display the union of those two intsets. All right, so where are you? Ah, yeah, okay. Well, the left one is the one on the left of the operator, and the right one is the one on the right of the operator. Ooh. And possibly, interesting question, commutator. So this is an operator where you can write either argument on either side. But yeah, you've got to say that the argument on the left of the operator is an int set, the argument on the right of the operator is an int set, and it's commutative operator. So I think you put the double pipe symbol there, but you can go and check that. All right, and here there's all this extra junk where it's testing that. We're not interested. We're not interested in doing this. If you want to do all this stuff, put it in a separate file, a separate SQL file. And once you've defined a type, you can then create a table with values of that type and run all of these sorts of tests on it. All right. Creating an aggregate function, I don't think we're being asked to do any aggregates in this context. One thing that you are being asked to do, though, if I go back to this, is that there's a function which tells how many elements are in the set. Now, that might suggest that it would be useful to store a count of the number of elements rather than having to scan. If you store it as a string and you don't have a count, you'll have to scan the string and count them each time. if you store them as an array of int values, you're going to need to know how long that array is anyway. So you will also have to be storing a length somewhere in your stored representation. Right, blah, 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 blah. Right, a whole bunch more operators, less than, greater than or equal, and so on. Define all of them at once. Yeah, if you want, you can, and in fact, it would be a very good idea to do something like this, to have a lower level function that performs various comparisons on int sets. And then all of these things, where is it? Int set abs greater than is simply a call, simply does a call to this function. Immutable, strict, where does it say that? Right, immutable, where's that gone? Strict means that the, good question, should have looked it up before I came. They're related to what effect the function has on the database. So if it's a read-only function, I'm pretty sure that's what immutable means. And strict, I don't know. Let's go and have a look. If you don't know what it is, go and look in the Postgres manual. All right, that's not useful. How do I get to the Docker base? What's this? Not that. And it's related to function, so it's going to be defined in the create function. All right, good-o. It's going to be defined in a create function definition, which is here. Create function. So you should be, I mean, one reason I'm doing all this is the kind of thing you need to eventually do. Strict, oh there, hold on, you did. Ah, strict is related to nulls, I think. Right, but so we can see that we can have immutable, stable, volatile, blah, blah, blah. I think volatile means that the function might change the database, and I'm pretty sure immutable means that it will never change the database. And stable probably means the database doesn't change over the duration of the function. So let's start looking down here. Immutable indicates that the function cannot modify the database. Oh, and it always returns the same result when given the same argument value. So it's like a regular function. Doesn't rely on the underlying state of the database. Stable means that it does rely on the thank you, Curtis. It would be called pure in some other contexts. And volatile means that the function result can change even if you pass the same arguments. Kind of makes sense in the context of the database if you're looking at parts of the database, or functions like this. Random current val time of day obviously change. Now strict, I'm pretty sure is, where's it gone? Oh, strict, colon null input, returns null on null input, yeah, all right. So if any of the arguments are null, the function returns null. Is basically what that means. So does that explain There's a question further back there. All right, so we create a bunch of operators. Please do not put this, I don't think we asked you to make indexes. Better check. As soon as I say that, we'll discover that we did. Oh, there's a few questions already. Why are they all red? I guess Dylan's been answering questions. How come I didn't see those questions? Interesting. Let's pop it up in the full browser. Much simpler. Where are we? Oh yeah, the other thing you'll need to do as well is that in the make file where you're putting intset.source and intset.c, you'll need to modify the make file so it understands that those files are relevant and need to be compiled. I can't remember what I was looking for. In any case, oh yeah, that's right. Did we ask you to make an index? I'm sure some of you could tell me. No, we didn't. It's kind of, indexes aren't so relevant for sets. Certainly for simple kinds of values where there's an obvious ordering involved, they are useful. But yeah, all right, so no indexes. So you can forget about this part. You can forget, and one thing we definitely don't want you to do is to leave something like this at the bottom of the file, because how could you submit? We haven't even set up the GIF spec yet, unless Dylan did it. Oh, I haven't. Dylan has. Damn, he's a good admin. All right. Yeah, do not put this at the end of your file, of your intset.source file, because when we try to test it, we're going to call the .sql file that's produced from this, and it will set up a data type for us. It shouldn't run any of these tests. We don't want that. So it shouldn't make any data at all. It should just create the type and all of the associated operators. If you stick this at the bottom of the file, then your lovely .source file will create a type, set up the operators, and then remove the type, which isn't at all helpful. And the reason for the cascade here, I guess, is to make sure that you clean up all the operators. But do not do that. Get rid of it. You can just comment it out, or you can even delete it. So there should be no examples involved in this. So basically, we just need, is the setup of the base function, the operator definitions, absolutely correct. So everything else you can ditch. So you'll end up with a relatively smaller file than complex.c. Now I know in the past people have submitted, when we've run assignments like this where they make a base type, they've submitted .source files that have drop type blah 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 at the end, which is slightly annoying. And because it's so annoying, we'll be docking marks if you submit a file that drops the type at the end, because then we'll need to go and fix your submission. So do you have to fix your submission, Curtis? Good. All right. So complex.source does all the SQL level definition for the type. All right. Intset.c. Oh, damn, I want to. It's probably not going to make sense on a lot of these. Just changing the name int set, but hey, that's all right. Right, oh, there's another thing. All right, so a lot of this stuff is boilerplate. You just got to make sure that you put this in, make sure that you hash include the appropriate stuff. Obviously, since we're not doing send and receive, then maybe you don't need to include that. One thing that you definitely need to do is to have some kind of definition for your int set type. And it's obviously not going to be a pair of doubles. And this is going to contain the representation. Yeah, sure. Oh, I've done .n, I still have no idea what, yeah, all right. So Curtis answered William's question. Contains the internal representation of, so whatever you decide to do ends up there. Right, and then of course we saw in the .source file that there were various functions that we defined. I have no idea what PG module magic does, just leave it there. If you want, no doubt it's a hash define. Yeah, it's magic. You can go and look it up. Hey, I wonder if ctags understands hash defines. Oops. There you go. It puts in some magic definitions. Oh, it's actually part of FMGR. I would have thought that was a file manager. Maybe it's function manager. In any case, it gives you definitions that, let's go back into here, that I think it gives you definitions that allow you to do these things. So there's got to be an interface between the SQL level, which you defined in the .source file, and the .o file, which is what's being constructed here. So this is going to be compiled into a .o file, which is linked into the Postgres server when it runs. And eventually, that becomes a data type that you can actually use in your Postgres applications. All right, once again, all your functions need to have that at the start. Okay. They need to have this definition of arguments. And then, all right, well, this is probably a fair bet of something that might be useful in your function, because the input argument is a string. So it makes sense if you do that, then what your function will have access to is the string that string, okay? So this is a string that's being read in and what you're about to parse to build your internal representation. And one thing to notice, it returns a datum, which is a Postgres attribute value, essentially. So you have to construct one of these datum things. Now you can see how these guys construct a datum. They basically just allocate some space to hold the object. They put values into the allocated space. Notice that Postgres uses palloc rather than malloc. And since this thing is a pointer, then they return a pointer value which is wrapped in a datum. I have no idea what the difference between palloc and malloc is. If you want, you can go and get a hold of the malloc source code, and you can also go and find the palloc source code and see. In fact, let's do that right now. See, maybe palloc just, yeah. Yeah. Wow. Oh, that's all. All right. So it's a version of malloc, which I assume, as Curtis says, prevents you getting any leaks, but you get leaks because you don't free stuff, not because you didn't malloc it. Interesting. I didn't know that Postgres did some kind of garbage collection. It probably doesn't. Okay, all right. So as Curtis said, it uses pools of memory. Good. See, could have all worked that out yourself by going and reading the Postgres source code. Or perhaps reading the documentation where it talks about internal, So our memory is managed internally in the server. So, so we know there's a buffer pool. That never gets freed. That gets allocated when the service starts. But in this context, we allocate a chunk of memory, I assume, and we use that for palloc. Wouldn't surprise me if this actually is a chunk of memory that's allocated for the server process that's currently running. All right, and then, well, when the server process is finished with that memory, it knows it's finished with it, can just free the whole pool chunk. All right. Don't know if that makes anything clearer, but all you got to do here is define all of these functions. So come up with your internal representation, and maybe there are there's a stored representation, and there's a representation that you use internally in these kind of functions that allow you to efficiently manipulate sets. So that's assignment 1. Defining a new data type. like I said, some of this stuff, it's just boilerplate. So, you just put that in front of all your functions. You define your function arguments like that. You actually extract the values of the arguments like this. And you can see how it's manipulating the arguments in here. So you can use, an analogous kind of approaches in your int set data type, but obviously not quite the same because int sets are variable lengths, and there are examples somewhere of creating data types with variable lengths objects. I always thought there was some in tutorial, but tutorial seems to have been gutted a little bit over the years. There may be examples, all right. Says Curtis, there are no examples of variable length data structures. However, oops, I had a feeling maybe you can find some examples in here. Yeah. I'm sure there are examples somewhere. Anyway, if someone finds a nice example, post it on the forum or something, and everyone can share in the discovery. All right. Where were we up to? Oh yeah. So that's assignment 1. Any other questions on that? I mean, a lot of the deal of this assignment is for you to discover this stuff yourself by looking at various sources like the tutorial directory, looking at the documentation and so on. Who knows, you might even find stuff online if you go looking for it. All right. And I'm not going to answer any more questions from people who say, my /server directory is not there. Yeah, it's not going to be there unless you put it there with priv server. Okay. All right. So this might be kind of relevant, although it's probably even lower level than what you need for the assignment. But let's have a look at how we might build tuples in Postgres. First thing, let's go and have a look at this function. Where am I? Am I currently editing anything? No. No. Oops. Wrong directory. All right. So here's the thing that builds tuples. So what we're given is an array of values. Okay. In C, we'd pass an array as a pointer. And you might say, how do we know how long it is? Interesting question. Not really, because that answer is going to be contained in the tuple descriptor. The other question that might pop up is, why do we have to pass a pointer to is null, or a pointer to a Boolean? And the reason is that we've actually got an array of Booleans which is the same length as the values array. And because there's no bit string that represents or that can represent a null value for every data type. If you think about the data type integer, every possible 32-bit string or bit string is a valid integer value. So the only way you can represent nulls is to have a separate indication that a particular attribute is null. So, you know, if the first value, say in this in a call to heap form tuple is null, then the first datum value is going to be a simple value of that appropriate type, which is going to be worked out from the tuple descriptor. But whatever we put in that is irrelevant because we're going to put is null as true for that first data value. All right, so this function, heap form tuple, returns a heap tuple. And if you go back and look at the slides, which I may or may not have accessible from here. Good question. In fact, very good question. And we can find out instantly, I hope, by using our tags file. And it's just size underscore t, which, if I remember, is an unsigned int, which seems a bit excessive because I can't imagine we're going to have any objects that are that big. All right. Right, so let's go back to heap form tuple. Yeah, so it returns a heap tuple, and if you go back and look at the all of the definitions in the Postgres tuple slides, you realise that heap tuple is actually a pointer to heap tuple data. So to a heap tuple data object. And we can go and look up the definition of that. But I think a little bit of it was given on here. Yeah, all right. So a heap tuple is pointed to heap tuple data. Heap tuple data contains length. It contains a self-reference, which I was never clear what that is, but certainly length is the number of bytes in the actual data, in the record, if you want to put it that way. The other thing that heap tuple data contains is a pointer to the, well, an OID, so you can reference the catalog data for this tuple. So you can find out all of the type information and the attribute information through that OID if you really want. And the final thing in a heap tuple is the data, the field called data itself, which is actually a pointer to the stored record, which is going to be sitting in a memory buffer somewhere, or at least somewhere in memory. Okay, and it's a pointer to heap tuple header, because what's actually at the end of this link, and it's really where these diagrams would be useful. Let me just see if I can, yes, beautiful. All right, so this is what a heap tuple is. It's a pointer. It points to one of these heap tuple data structures, and T data is a pointer into the memory where the actual information about the tuple is stored. Now, the information obviously contains the data values, unless they're toasted, in which case they'll be in another file. And what data will have is a reference to the toast file. And it also contains a header. And the header is one of these heap tuple header things. So we've got nested data structures. All right, and a heap tuple header is actually a pointer to a heap tuple header data object, which contains yet another data object called heap tuple fields, which is that thing there. Oh yeah, this is a version pointer. So if this tuple, if there's a newer version of this tuple, so maybe we've done an update and this is the old version of the tuple before the update, this will contain a reference to the new version. And then there's a couple of masks which contain various information, various things like, does the tuple have null values in it, and so on, which would affect the size of the tuple. And it would also affect whether we even need this array here, because this array here tells us which components of the tuple are null. And TOFF is the offset from the very start of the tuple header to where the data actually starts. And the reason we need an offset here is because the length of this thing is determined by the number of attributes in the tuple. And so this isn't always going to be the same size. And so TOFF actually tells us how far we need to go before we find the start of the actual data. And the start of the actual data will be the first datum in the array of attribute values. Right, other things that we find in the heap tuple, the transaction that created the tuple, the transaction that deleted the tuple. Obviously, as soon as we create a tuple, this value isn't going to have anything deep in it. And it's probably worth I'm now putting it's worth having a look at this thing. I might just jump to the next slide here. This one to show. So this is the entire header that we're dealing with. And these items at the top here are the heap tuple fields. I don't know why they split everything up like this, but rather than just having a single heap tuple header data with all of this stuff in, but they did. All right, so you can see the heap tuple header data is this stuff here. Bits is a bitmap for all the null values, and then we have the actual attribute values following on directly in memory. So you've got to imagine that attribute 1 is followed by attribute 2, is followed by attribute 3, and so on. The one reason I wanted to show you this is it actually contains a union. So this field, T field 3, serves two purposes. It could be the command ID for the command that either inserted or deleted the tuple, or both. That's interesting. I don't know how you can insert and delete at the same time. Or it could contain information about the vacuuming of that tuple. So this single field has two different purposes, and you access the different faces or whatever of this field by using the appropriate name. So it will be interpreted differently depending on the name that you use. But obviously the first two fields are transaction IDs. All right, let's go back. I think heap form tuple. And I think I could have done that because there's a stack of tags, but there you go. All right, so we sort of look down into all this stuff. And where it says that that's the tuple data, it's actually, well, it's the header followed by the actual attribute values. All right, so len, I assume, is going to be the total length of the record, header plus data, and data len is obvious. It's going to be the length of the data part of the tuple. All right, number of attributes we can get from the tuple descriptor. Okay, so this is going to tell us things about the tuple, and we'll have a look at what they are in a minute, but certainly one of them is the number of attributes. And initially we assumed that there are no nulls in the tuple, so we set this flag to be equal to false. And well, there's an integer for doing iteration, I assume. I guess it's possible you can have too many attributes. It seems a little bit strange to me, but I guess you can. And then we iterate over all of the attributes. For each attribute, we check whether it's null. Where did that come from? Oh yeah, that came from this array. Okay, so this is an array of Boolean values to tell us whether particular attributes are null. And if we find any attribute which has is null true, then we set has null equals true. So now we know that the tuple has at least one null value in it. Okay, so the length, we can compute offset of heap tuple data and t-bits. It's hard to tell when you've got these functions or macros that are doing things. I won't bother going and looking at that, but let's assume it can compute the length. All right, there's a little bit of alignment that we potentially have to do as well. Basically, alignment means if you've got an integer value, you can't start it on an odd byte boundary. In fact, you have to start it at a byte address, which is multiple of 4, assuming 4-bit integers. All right, then to work out the length of the data, we actually have to go through the data and look at all of the values and work out how long each value is, because the information about how long the value is stored in the datum itself, I believe. Or certainly you can extract information about the size from the tuple descriptor. Whoa, got mad here. Where are we? Oh yeah, all right, so this length that it's computing up here is basically the size of the header. If we go back here, it's how big that bit is, including the bitmap for the null values, and then we compute the total length of the data items, and then the whole length of the tuple is that. So we work out the length of the header and work out the length of the data, and then we add the data onto the length of the header. That gives us a total tuple length. All right, allocate the space that we need. Heap tuple size. Oh yeah. No, I'm not sure what heap tuple size is. So this is me exploring this as we go. But I'm guessing I can explore it faster than you can. Okay, right, so yeah, I kind of thought that. It's the size of the heap tuple data, which is this. All right. Can I go back? No. Good. This is where C tags fails when you can't remember the name of the thing that you're looking for, but I expect CScope may have the same problem. Yeah. Right. Blah, blah, blah. Da, da, da. So we've worked out whether there are any nulls. We've worked out how large the whole thing is. Ugh. All right, everyone use CScope. It's clearly superior to CTags. Yeah, so the heap tuple size was the header, and that's the total size of the tuple, and we're actually allocating space for both of them. Interesting. Yeah, indeed. Right. Right, so we said tuple, remember one element of tuple is the length. So we've computed the overall length of the record. What's an alias for tuple data? Oh, all right, fine. Oh, yeah, all right, you're talking about that. Yeah. So we've got a pointer to the actual tuple data in memory. And all right, so, and we've got the length. So let me just go back here. Item, yeah, I've been wondering about this. What is this? Oh, good. All right, so we set it to invalid initially. And the table ID, all right, we also set that to invalid. So I guess that's just to initialize things. Right, so now we're looking at the tuple descriptor, which, if you remember, was the first argument of this function. Okay, tuple descriptor. So I think we need to have a look at what's here. So this is really just to give you an idea of the kind of data. So once again, a tuple descriptor, we see this in a lot of instances in Postgres. Tuple desc is a pointer to a structure which contains the actual data, and the structure is defined right here. Tells you how many attributes there are. It's every time you define a table, you also get a tuple type defined, which is, well, they call it the composite type for tuples within that table. Type mods, I'm not sure what that's used for. I guess we could go and look in the manual, but I don't want to. Reference counting, interesting. What I was more interested in than these two fields are these ones, right? So this is an array of constraints where each constraint would apply to the corresponding attribute. So the first entry in the constraint table would be a constraint for the first attribute, and so on, and so on. And then we have another array which tells us information about each of the individual attributes. And this information is gleaned from the catalog data. And if we go and have a look at the definition, why is there not a tag? It's clearly a type. Sure, I found it before. Oh, there's no point asking again. So here's the other disgusting hack if you can't work out. Use grep minus r, starting from the current directory. So recursively look at all the files in the subdirectory to see where this is mentioned. And it's probably mentioned in a few places. So we pipe it through less, and it seems to be mentioned in a lot of places. Looking for a place where we might find the definition. Doesn't look like anything so far. Right, looks like that might be somewhere to look. Okay. And what I'm kind of hoping is that I lost it. I kind of think that this might actually be it. Wow, what a great definition up the top here. Woohoo. Interesting. I wonder how it knows that we don't like magic numbers, do we? But I suspect if we were to go to our Postgres server, we would discover that that was an OID for one of the catalog tables. Let's have a look here. Really? I'm banking on this being a table. All right, surprise, surprise, it's the PG attribute table. And I suspect if you were to go to your Postgres server, you would find 1249 is always the PG attribute table. Now, I kind of think that this right here might be the definition for form data PG underscore attribute. So you can see that it's certainly related to the PG attribute table. What's the relation that this attribute comes from? What's the attribute called? What type does it have? How long is it? That, of course, suggests that this would only apply to fixed length attributes. If we've got variable length attributes, then that value isn't going to be particularly useful. The attribute number, so which position, is it the first attribute, the second attribute, the third attribute, and so on. You can see the amount of comments that we've got here. So in some contexts, Postgres has a massive number of comments, which are generally quite useful. If it's an array or a matrix, then how many dimensions does it have? If it's not, then that's 0. And I think I mentioned this on the video, that this has a huge number of, well, it has a very long definition, partly because it's got so many comments. All right, but lots of information about attributes, which I suspect comes from the PG attribute table. Yeah, so if we started looking through that definition, I think we'd find most of these attributes. Certainly we saw name, certainly we saw the type, we saw rel ID. So I guess that form data PG underscore attribute is basically just a copy of the relevant information from the PG attribute table, which and I said somewhere in one of the videos that a tuple is essentially just a byte string. You need to be able to interpret it, and this is how you interpret each of the individual attributes in the byte string. Because we need to know where the individual attributes are. We've got length information that will tell in the tuple header that will, length information in the datum that will tell us how long each of the attributes is. So, all right, so chasing down rabbit hole after rabbit hole, we can eventually get to the point that we've got tuple descriptors that tells we've got an array of catalog information about each of the attributes, which I suspect if we were to look at trying to interpret the individual attribute values, that would come into play again. So we can have a tuple, but we would also need one of these tuple descriptors to interpret the values. All right, that was an interesting rabbit hole. if you want, you can trace your way through that code for the heap form tuple function to see precisely what it's doing. All right. Now, this isn't exactly Postgres tuple structure. I think I used this field descriptor. This is kind of like what we were just looking at to some extent, a much simplified version. So what's the offset of the field in the data? How long is the field and what type does it have? So the question is, I've written these things just as triples here. If we're actually trying to do them as data structures, how many bits would we need for each of these components? So the offset, the length, and the type. All right, so we assume we got 8K pages. Let me see. I have somewhere in here. I think it might be, yeah, all right, in here. Okay, so how big is one of these field descriptors? So this thing here, how many bytes or how many bits do we need to represent one of them? And we try to obviously do it as compactly as possible. Right, so potentially they could be 8 bytes long by doing a little bit of packing, right? How do we do that? So if we're talking about offsets, pages are 8K bytes, so clearly there can't be any offset that's longer than 8192 minus 1, and in fact they're going to be even smaller than that, because if we didn't have an offset that was 8192 minus 1, that would imply there was a tuple that started right at the top of the page, which there isn't going to be. But to represent this many offset values, 13 bits is sufficient. All right, representing tuple lengths is how long is a tuple, how long is a piece of string. It wouldn't make a lot of sense, and it's certainly not possible for a tuple to be longer than a page. Postgres makes that distinction. Where's that? Okay, fine. It's minus 1 byte, I guess. But the minus 1's kind of immaterial here anyway. We need 13 bits to represent the range of offset values that we need. All right, how many bits do we need to represent the length of an attribute? Well, like I said, an attribute, oh, these are records. Oh, no, they are attributes. They are attributes. So what's the longest attribute we could have? Well, it's certainly got to be less than the size of a page, because records can't span pages. And I've suggested here that maybe maximum length of attributes 2K, even that sounds a little bit generous. But I know that Postgres has built into it somewhere what the maximum length is. And I think it was mentioned in one of the videos. Yeah, all right. So if it is 2K, then we need 11 bits to represent that. Now, of course, we have attributes that are larger than 2K, and we know that they end up being toasted, and so we end up storing them using some kind of more compact representation, basically just a reference to the toast file. So they're clearly going to be less than 11 bits. What's the relationship between all those things? Have a look at the slide, it shows you. Or have a look at the video for Postgres tuple representations, because it tells you. Where the 32 bits come from. Oh, okay. I've assumed that record IDs are 32 bits long, which is probably adequate. Remember that a record ID consists of a page ID plus an offset within the page, or a tuple index within the page. Interesting question, is 32 bits enough to do that? If files can be 1 gigabyte and a page is 8K bytes, how many pages can we fit in a file? Who knows? Who can do the calculation? What's a gigabyte? 1, 2 to that. That looks like 4 gigabytes, is that right? Yeah, all right, so maybe. Looks good to me. To the, what? To the 17? Oh, okay, thank you. Right, so overall, about 128K pages is the maximum number of pages. And since Curtis has been kind enough to say what power that is, 17 would be the number of bits to represent the page. And then the offset within the page doesn't actually need actually, that's an interesting question. I've talked about offsets requiring 13 bits. Oh yeah, okay, 17 plus 13 is 30 bits. So therefore, if we allocate 32 bits, that should be sufficient. All right, types, we need to store an object ID of a tuple, and that would also be a 32-bit quantity. Now, of course, so we've got the offset, which is 13 bits. We've got the length, which is 11 bits. That's 24 bits. That's how 7 doesn't 2 to the power 17 is 128K. Yeah. Yeah, so we got 24 bits here. Oh, that's nice. That's 3 bytes plus if we have variable length attributes, then maybe we need more bytes than that. So, all right, it looks like 4 bytes plus an OID, which is another 4 bytes. So it looks to me like each of these things is going to be 8 bytes long. So you're partitioning the bits up. It's not exactly. So set the second 32 bits is going to be the OID to the catalog table that contains type information. The length, we know 11 bits needed for that. The offset, we know 13 bits needed for that. Therefore, 13 plus 11, 24 plus 32. So if you could, if you really wanted, if you weren't worried about alignments, then I guess you could have 7 bytes. But I suspect that we're going to need 32 to get the alignment right. We're going to need 32 bits, so 4 bytes plus 4 bytes for that. So 8 bytes for each of these things. If it turned out that an OID wasn't 32 bits, then maybe these could be more compact. Certainly we want to keep these things as small as possible, since to some extent they're overhead. All right, let's have a look at the next one. Oh, hash files. Didn't talk about hash files, but I hope that you remember hashing from your data structures course. Basically, with hashing, you take the key value that you're looking for and you compute an index. So if you're talking about arrays, you take the key value, use a hash function to compute an index, and that's where you'll find the key value that you're looking for. Or you may not, and you may have to do linear probing or various kinds of rehashing. In the context of a file, then we're not going to do rehashing or linear probing. What we're going to do is, if we fill up a page and we need to insert another tuple into that page, then we add a page to the overflow file, connect it to the original page, and store the new tuple there. Yeah, you can call it a hashed index if you like. There's no actual index structure. All we need is the hash function to work out which page we're dealing with. All right. So what have we got here? 10 pages, 10, and this is 10 primary data pages. Plus, we can see that there are some overflow pages. And this page here has 2 overflow pages, because apparently there's a lot of keys that end in 1, the digit 1. But not so many that end in 2 or so on. All right, and here we got this slightly unrealistic assumption that each page only holds 1 record, only 1 record, 4 records, and each record has a key, and all we're actually showing here are the key values. But each of these small squares corresponds to a record. All right. So if we wanted to answer this query, we would run the key value through the hash function. That would give us the number 1. Doesn't actually have to be a primary key, although, no, it doesn't have to be a primary key. It's possible that we could have, k equals 51 here as well. If it was a primary key, then, well, we're going to end up with the same hash value, regardless of whether it's primary key or not. We'll end up with the hash value 1, so we go to page 1. We have to look in here to see if there's any tuples that have k equals 51. In the primary data page, there aren't. B is the number of data pages, so 0, index from 0 to 9. Oh, it'll be whatever attribute you choose or whatever combination of attributes you choose. We'll be talking about multi-attribute hashing later. Here I'm assuming that we're hashing on a single attribute, which looks from this data like it's a primary key. All right, if we know for sure that it's a primary key, we look through this page, we don't find any tuples with k equals 51, which is what we're looking for. So we go to the first overflow page, and as we look through here, we find a tuple with k equals 51, and we're done. By the way, C is the capacity of a page, and looks like from this diagram that each page can hold up to 4 tuples. How will it return in the overflow page? Well, it won't. All it's got to do is find a tuple, and it returns the tuple. Doesn't matter where the tuple is, whether it's in a primary data page or in an overflow page. All it's got to do is find the tuple. Now, if it return tuple 1, no, what's tuple 1? It's going to return this tuple here, which has the appropriate key value. So all I'm showing here are the key values, not the rest of the tuples, and certainly not tuple numbers. If you wanted to talk about tuple IDs, then say this tuple here would have page ID of 1 plus the tuple index of 0. So those two things together would give the tuple ID for this tuple. Interesting question what you do about overflow pages. All right, getting back to Curtis's point, if this wasn't a primary key, once you found k equals 51 here, you couldn't stop. You'd need to keep looking in case there was another tuple that also had the value k equals 51. Obviously that one doesn't, that one doesn't, that one doesn't, that one doesn't. But if there happened to be k equals 51 here, then you would also find that. So that's if we've got a query where we're asked for a key value being equal to a particular constant. Means we can use the hash function. We can go straight to the appropriate page, but of course we have an overflow chain to consider as well. All right, so the best cost would be if the tuple happened to appear in the primary data page. So if we'd actually been searching for k equals 31, then we knew that k was primary key, then we'd read this data page and we'd find the tuple that we're looking for, and that would be it. We would have finished our search, having read a single page. So that's the best case, and that would apply to any of the pages. So for this example here, if we were searching for k equals 39, the hash function would tell us to go to page 9, and we look through the doubles here and we'd find k equals 39, and we'd be happy. If we were searching for k equals 99, then we'd still go to this page and we'd scan through all these tuples and we wouldn't find one that has k equals 99. So we wouldn't return any tuples. The worst case scenario where you actually find something, or where you don't find something, can the tuple be duplicated? In theory, yes. And Curtis's question before basically was kind of related to that. Can there be multiple tuples with the same key value, and there's no reason that there can't. So here, all you can see is that there's a tuple that contains the key value 51. You don't know what the rest of the tuple is. It's possible there could be another tuple here that contains key value 51. Does it have different values for the rest of the attributes? Maybe it does, maybe it doesn't. All right, so if we happen to be searching for, that's unfortunate, k equals 101, all right? 101 mod 10 is 1, so we go here, we look for 101 as a key, didn't find it, go to the overflow page, look for 101, don't find it, look in this page, look for k equals 101, don't find it. So the worst case, the maximum possible cost, is if we happen to hit the page that has the longest overflow chain. And in this case, it's this overflow chain here. If you happen to hit a page that doesn't have any overflows, then all you've got to do is read that page. You know, if we were searching for k equals 100, we'd go to page 0, no k equals 100 here, we'd go to this overflow page, no k equals 100 there, so we're done. So we had to read 2 pages. In other words, you have to read the data page plus all the overflow pages associated with that data page. So that's the worst case cost. Best case cost is you happen to find it in the primary data page. Worst case cost is you read the entire overflow chain, and you're unlucky that you hit the page with the longest overflow chain. All right, so that's k equals 51. What about this query here? If you look at the contents of the file, you can see that the order on these tuples is pretty random. So hashing doesn't help one iota unless you know the exact value of the key that you're looking for. So k greater than 50, well, it has to be greater than 50. Well, it's a coincidence. Nothing in there is greater than 50, but we certainly have some here. We don't have any, well, it's a coincidence that it worked out that way. So basically, if you've got a query like this, hashing doesn't help you one bit. So if you've got a hash file and you ask a query like that and you try to solve that query on a hash file, then you get nothing from the hashing, and you basically have to do a linear scan of the entire file. So you look at this page, is there anything greater than 50? No, there's not. Look at this page, anything greater than 50? No, there's not. I should have made it greater than 40, so we actually found a few things along the way. In any case, so we can look at these 2 pages and find no matches. We could then look at this page, no matches there, go to the overflow page. There are a couple of matches, well, there are 3 matches. Then go to the next overflow page and we'd find more matches. We then go to the next data page and find no matches, and there are no overflow pages, so that'd be it. Then we can scan all the other data pages and their corresponding overflow pages and eventually reach the final page. Look through that, there are no tuples with k greater than 50, so there are no matches here. But on the way through, we would have found a match here, 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 and here. All right, the cost of doing that regardless of the value here, is and it's to do with the fact that we've got a non-equality operator. The cost is always going to be the cost of reading every page in the file, including all of the overflow pages. So in the case of a hash file, queries like that don't help you at all. The file may as well not be hashed for all the benefit you're getting. All right, so that's 4 o'clock, so we may as well stop there. And I'll see you on Thursday. Okay, so stop screen share and